Okay. We're going to do another tutorial today. Um, but first, let us take a couple of minutes to explore some of the tools that we didn't see last time that can be used for helping our development of lean code, and in particular, helping us to explore the library. So these are the tools that we've seen the other time. They are, some of them are necessary to, for example, use Lean on your computer, or to interact with other people, or some other tools can help you do some things like GitHub Copilot can help you write code, or Lean Informal can help you translate your code. Now we're going to see some tools that help us look into the various libraries that exist. In particular, we're going to be interested in looking into the Mathlib library, which is the main mathematical library that you want to use when developing some Lean code. So let's start with the most canonical source, which is the actual documentation of the library. Now it's usually called the API documentation, and it's automatically generated from the code in Mathlib. Let's take a look at this. Okay, so this is the homepage of the API library. It's a bit strange because it looks like you have some random series of characters here, but that's the normal look of the homepage, and this is just an identifier that tells you which commit of Mathlib, so which version of Mathlib you are into at the moment. That's usually the latest version of Mathlib. And it has such a long name because this is basically the Git identifier for the commit. And we have multiple commits a day to Mathlib. So the library changes many times during a single day because many people contribute new code, and not every single contribution gets merged alone. They are the different contributions are usually backed into like a group of like 10, 20 contributions, and then all of them get merged together. But for example, if you try to contribute to Mathlib something, you're not going to see your code merge right away when it's accepted, but in a couple of hours, it will be probably even less than a couple of hours. So what if we want to just explore how the library is made? We can go here in the left part. In particular now, there are some releases of Mathlib. I'm not sure how frequent the actual version changes. Now the lean version changes around once a month, roughly. And maybe Mathlib tries to keep up with that in some way, but basically it continuously changes during every day because new code gets merged. Yes, not only during the different releases. We can probably, there's if you go to GitHub Mathlib for the okay, no, there's no version here, but there's some. I think there is somewhere. For example, in the link for web, you can see here there's like there's the stable version of Mathlib, and then there's the actual latest version, depending on whether you want to have like the very latest lemmas or you care more about stability and absence of bugs. Okay, so as I was saying, this is the main tool if you want to just look for a specific lemma. And you have two ways of browsing it. You can look here on the left. You have all the various directories of the library, and we have both Mathlib and the actual Lean code. Now, most of those things are not going to be interesting if you just need a lemma. For example, there's ESOP, archive batteries. These are all files that are useful, but probably not useful directly to you when you program in Lean. Most of things that will be useful are going to be in Mathlib itself, where you have all the various branches of mathematics. You can go in again, and then you have the files. And all the files are organized like this. You have a series of, in this case, we only have definitions because apparently this file only has definitions. Let's try a different file. Okay, this file has not only definitions, you have definitions and theorems. And usually you have some kind of description of the file at the start. Then each definition or theorem has its own box where you can see the statement, the formal statement, and a comment that's associated to the statement, but not the proof, because that's usually not useful just to when you just want to browse your files. Of course, there's still a way to look at the actual proof. You can just click on source, and you will go into the actual GitHub page of this specific Mathlib page, and you can see like all the code. So now the proofs here are all very small, but this is the proof of this theorem, for example. Now that's not usually how you browse the library, though. You don't know where you want to look because you usually want to search for a specific result. So you will not try to browse the library manually. You will write some identifier that you think is related to the name of your theorem according to some notation. Usually, for simple theorems, if you have some experience, you can more or less guess the name out of the box. For example, let's look for a very simple lemma about the commutativity of the addition. We'll write something like add com, and we have all lemmas that contain add com here, and we can just click on it and get the result. So that's usually the first place where I want to look if I already more or less know what I'm looking for, or at least if I know the names of the objects that I want to look for. Now, another useful reference is the Lean reference. That's mostly useful if you want to know something more about the Lean language itself, maybe some keywords. It's mostly for more low-level stuff that what you will need during your proof development, but sometimes it can be handy. For example, if I want to see simp, which is one tactic, maybe I want to know the specifics of the actual tactic, or maybe the arguments I want to give to simp. But these are things you probably not need at the start. What instead you will need is a tool that's more powerful than the actual API, because maybe you know what you're looking for roughly, but you don't know what's the correct notation. You don't exactly know what should be the name of the lemma you're looking for. So you need some search engines for the library. Now there's a couple of choices. I will just list them and quickly go to a website of a couple of them. Now the first one I'm listing here is Moogle. That's basically a semantic search, so you can look for something in natural language, and it will try to give you a list of results that are similar to your query. I'm not going to show this because it's just similar to the others, actually. Now Loogle is a bit different because you actually search for the specific signature of the theorem. So you're not going to write something like I don't know, the theorem of the fundamental theorem of algebra, something like this. It's not going to take it as an input. It's going to take a pattern as an input, and that's useful when you want specific formulas. For example, what if I want, let's say I don't know how the commutativity of addition is called. I want to look for it here. I can write it like this. A plus B equal B plus A. And if we look for this specific pattern in all the Mathlib library, now you have to put the question marks before. Now it's not. It's just taking a bit. to load the website. Now you have to put the question mark before each variable if you want to give the variable name in Google. You can even just forget about the variable name. Okay, now let's look for Google again and see if it works better. Okay, it seems like Google is okay. No, it works. Okay, so I could do something like this without the variable names. And if we look for this pattern, but of course it will not know that I want to swap the variables. So it will just look for any pattern where we have a sum and another sum on the left-hand side and right-hand side. So that's quite powerful if you're looking for something very specific. But a lot of theorems do not fall into this bucket. So you're going to use, for example, Moogle, or even better, lean search. Okay. I'm going to look at this. Lean search is similar to Moogle again, and in my experience, it's a bit more updated frequently with the latest Mathlibs, and it works a little bit better. So I would suggest it over Moogle, at least for the moment. Now these tools get updated quite frequently, so the best tool changes over time. But here in lean search, I can look for and theorem algebra, and it will give me some reasonable results here. For example, now it gives me both the name of the theorem, the statement of the theorem, and some AI-generated description of the theorem. And I can both jump to the doc. So clicking here, I'm going to the API documentation of the specific theorem. And from here, I can, of course, again, go to the code. That's usually useful if you're looking for a result. It gives you some suggestion that's not exactly what you want, but maybe the thing that you actually need is on the same page of the API documentation. So you're going to maybe jump to that result and then look around a bit in the page. And if you're lucky, you'll find your theorem. Now, another tool that exists since not so long ago is lean state search. This is yet another way of looking for things. In fact, this does not take a natural language description of what you need, but it takes the context you are in, and it tries to suggest lemmas that can be useful in that context. So you're just going to go in the, let's say you have your, okay, like here, you have your info views inside some kind of theorem. You can just, okay, here it's stopped. You can just basically copy paste whatever is in the info view. Let's go here. We're going to have all our info view. We can just copy this and then go to lean state search and just paste it here and do search. And that's going to, again, suggest us some theorems that may or may not be useful. Now, the last tool I want to show you is Lean Explore. Again, I'm not going to jump into the web page because that's basically the same as Lean Search. It's the same idea. You just do a natural language query, and you get some suggestions of lemmas that more or less match your query. That's out, but just like it was put online just, I guess, 2 weeks ago or something like this. So it's very new to Lean Explore. Okay, great. So these are your options mainly if you're stuck in a theorem, you're looking for something and you don't know the exact name of the lemma, which is most of the time because we usually do not memorize the whole library. So if you actually do some proofs in Lean, you're going to use at least one of these tools quite a bit. Okay, now I think we can go again to the actual tutorial. And so last time we did the first 2 pages of the Glimpse of Lean tutorial. And if I remember correctly, we didn't look at the exercises of the second page. So if anyone wants to look at the exercises or has some doubts about them, please tell me. If not, we're just going to review very quickly the tactic that we've seen last time, and then go on to the 3rd and 4th pages. Okay, so maybe we can do it like this. So let's start just by refreshing ourselves the first two files. And let's just go to the end of the file to remember which were the tactics that we introduced. So we had ring, which allowed us to solve automatically problems that included swapping variables or associating variables. Basically anything you can do within the axioms of a ring. We have rewrite that allows us to take a lemma that has the form A equals B and substitute A with B inside the goal, for example, or inside the hypothesis if we use rewrite at. We had exact that lets us give the exact solution to the goal. So if we somehow manage to come up with a proof term, so maybe a lemma, an external lemma, or an hypothesis that solves the goal, we can use exact. And we had calc here that allowed us to do this kind of stuff. So we start with some expression, and we do a series of equalities that modify the expression until we get the final result. Okay. In the second file, we introduce four other tactics. We have intro, which is used when we have a goal of the form A implies B, or a goal of the form for every A, P of A, for example. Intro allows us to introduce either the variable A, if we have a for all, or the hypothesis P, if we have P implies Q. Apply is a stronger version of exact. It allows us to both close a goal, but more importantly, it allows us to use a lemma without having to give the hypothesis to the lemma. So we can just say, okay, we're going to use this lemma. Please let me prove the needed hypothesis after I applied it. And it can also be used for forward reasoning. So we can apply a lemma to some hypothesis to modify it if the hypothesis matches the hypothesis of the lemma, and then it will get converted to the conclusions of a lemma. Have is another tool to do forward reasoning. We can introduce new hypotheses with have, and then we prove the new statement that we declared there. And then finally, we have constructor that is used when we have some goal of the form A and B. And it basically splits the goal into prove A and then prove B, into two separate goals that we can prove separately. Okay, now we can go on to the third file of exercises. Now the third file, we introduced the universal quantifiers, and that's basically the for all quantifier. We'll see how to use it into an hypothesis and how to solve it when there's when we find it into the goal. Okay, let's look at the file then. It starts by defining something. We give the definition of what is an even function. So it just says that for every x, f of minus x is equal to f of x. So very simple definition, but we have to use the for all quantifier. Now that's actually the same. We could have written the same definition, just putting the x not within the for all, but here we could have put the x in. That this time we have to declare what's the type of x, and we could have deleted this. That's exactly the same definition. It just takes some x and gives you back this proposition. Before it takes an f, but it already took an f. So you can write something like this. Okay, let's go back to the to that other formulation. Now Lin was complaining when we changed the definition because we basically put some explicit parameter. Let's see if it's true or if it was some other error. Let's see. Okay, no, it still complains apparently. Okay, yes, because it doesn't know how to. Okay, basically it doesn't know how to match the x with some argument. In fact, it says I don't know how to synthesize the implicit argument x, and it doesn't understand that it should just wrap everything into a single statement. So we want to say that for every x, this holds. But for some reason, it doesn't manage to understand that that's the thing that we want, and it tries to force the implicit argument to something, but of course it doesn't know what should be in there. Okay, so let's go back to the for all definition, and let's see how this can be used. Now this is a quite standard result that we want to prove once we define what is an even function, which is if we have two even functions, then the sum is still an even function. And what we do here is we start by using this unfold tactic. Don't remember if we already saw that in the previous files, maybe not. But the unfold tactic basically is something that's mostly useful for us humans to unfold a definition into the actual proposition. So instead of having here written even fun, if we do unfold even fun at HF, we can go over this line and it gets unfolded into the actual proposition that we called even fun before. Now, in most cases, this doesn't really affect the proof. That's not true. That's not always true. Sometimes it does. But I think that here, for example, let's see if it's true. If we just if we just comment out all the lines where we see unfold, the proof works the same because Lean internally knows that when it sees even fun, it just needs to treat it as if it had this proposition written instead of even fun. But for us, it's more convenient to have it spelled out sometimes. Maybe we don't remember exactly how we defined it. So the first thing he does here is it just unfolds even fun everywhere. It does this in 3 passages. It could have been done just in one line, like this, unfold even fun, and then we write at. Now, just like with rewrite, if you write nothing, it is implied that we're doing something in the goal, okay? While if we specify at, we can do this same thing, but in the hypothesis. So we could write at HF. We can write more than one hypothesis, so we can write also HG. And if we also want to specify, okay, do this same thing also in the goal, we can write /goal, okay. And it gets converted into this Unicode symbol, which is also here, which represents the goal. And you see, it does the same thing. So it unfolds the whole definition, the definition in all 3, in the 2 hypotheses and in the goal. Okay, let's comment this line. Now, what we do here is we use intro again. So as before I said, intro can be used both for the universal quantifiers and for the implications. I guess in the previous files we only saw that for implications. So we only introduced the first part of an implication, and in order to be used to be able to use it as a hypothesis. But the same exact thing can be done when we have a for all statement. So if we do intro x, we're introducing the x which was inside the for all, and then we just need to prove the statement for this specific x that we introduced. Now here, of course, now in this case, we're giving the same name that we read here. So here, x is called x, and we're calling it x, but that's just a case. That's not needed. We can give any name here, and we just need to use this new name as a variable now, and it also gets substituted in the actual proposition that we need to prove. Now this proposition is just a very simple series of equalities. So we can do it with calc. And the first thing we do is we split f and g. So we have f plus g computed at minus x. And we want to see that as f at minus x plus g at minus x. Now the way it gets done here is with RFL, REFL. REFL is the most basic tactic that there is, because it's just saying, okay, this is true by reflection, meaning that the two things on the left and the right of the equation are actually the same thing. I mean, Lin should already know that these two are the same thing. And in fact, this is very obvious statement gets closed by reflection, because the addition of two functions is really defined like this. If I do f plus g, this is the function such that when I apply it to some y, I just get back f of y plus g of y. The other two steps are, we already know how to do them because they use just rewrite. But it's interesting to see how the hypotheses are used, because we have an hypothesis with a for all, and how do we handle it? How can we use it? Well, that's very easy, because a for all is just a function. We saw on the first lecture when we saw what was like some details about dependent types. We saw that a for all is just a function that takes some element of a type and gives us back something that is not on a fixed type, but is inside some type which depends on the input. And that's one of the reasons why we are in dependent type theory, because functions can, like the codomain of a function can depend on the specific element that we take from the domain. But that's very useful to use propositions, because we can apply them as functions. In fact, we say that hf applied to x is just this thing applied to x, so it's the proposition with this x. There's not just a generic element of R, but is this specific element of R that we introduced at this point. We could have written something like hf of 0, for example, if we wanted to substitute 0. Of course, that's not the case, so it doesn't work inside the rewrite, but we could have put any real number or even an expression that has R as its type, so an expression of type R. Okay, so what we do is in here is we just substitute the definition of even function for f and the definition of even function for g. And then again, we use reflection because we have basically the same goal as we had here. We're just spelling out the definition of a sum of functions. Okay, here, sure.
But there we must put the x, or the right hfx, or even if we don't put the x.
We don't actually need to put the x. In this case, Lin can understand on its own that the only thing that makes sense there is x, because we only have, I mean, hf has on the left of the equation something of the form f of minus something. So Lin will look here, for example, it will look here inside the goal for something of the form f of minus something, and it will only find f of minus x. If we have more occurrences, Lin will just try to match the first occurrence usually. So maybe it will not do exactly what we want. So in some cases we want to, maybe in some cases it still works, but it doesn't do exactly what we need. In some other cases, maybe where we have more complicated expressions, Lin may not be able to understand on its own that actually there is something that matches inside our goal, and so it will ask us, okay, I cannot, I'm not managing to fill in these meta variables. Please provide them to me. Okay. Here it tells us that some tactics automatically unfold definition. This is basically what I was telling before, that you don't always need to unfold stuff by hand. You can, most things will get unfolded by Lin itself. Sometimes even when you don't exactly want them to be unfolded, but mainly it's something that you're mainly okay with. It will mostly be handled without you even knowing what's going on. It will just fill in the variables and give you the needed result. Okay, let's go into the next example. And again, we're going to use intro, but this time in a more similar fashion that we saw on the previous file, because we have some implication. And we just introduce here, we have a double implication, and we introduce everything at once. You see, we can actually compose the introduction of implications and the introduction of some parole, for example. In this case, we're doing everything at the same time because we're introducing HF, which is the hypothesis that F is even, HG, which is the hypothesis that G is even, and then Lean is automatically understanding that the goal that we want to prove, which is even fun F plus G, just means for all X something something. So we introduce that specific X just like we did before. So this is basically the exact same theorem that we've proven before, but it's just spelled out in a slightly different fashion. And the proof is basically the same as before. Again, we're just compressing all the results in one place. Actually, here we also see that we don't need the last line of the calc. You see here, before we had 4 lines of calc, REFL, 2 rewrites, and then REFL again. Here we start by REFL, we do the 2 rewrites in the same line, and then we don't need to do REFL again because calc will try to match automatically the final thing that we give with the actual stuff that it's proven inside here. Okay, here we have F plus G applied to X, and while here we're spelling just F of X plus G of X, but they will get just, it will understand that they are the same. Okay, again, we have another example, another exercise that you can try to prove. Maybe let's do this at the end of the file. Mm-hmm.
Since REFL is supposed to be something that we didn't understand, so I think can we prevent
let's see if this is feasible. Let's see if we give it the specific signature here. Okay, here it's probably going to complain about the indentation. Okay, no, it doesn't manage. Let's see why. So it tells us that the tactic rewrite failed. It didn't find an instance of the pattern in the target expression. So it's looking for something of the form F of minus something. Let's see what the goal is. The goal is F plus G of minus X equal Fx plus Gx. So in this case, rewrite doesn't find anything that's written like F of minus something. And so it doesn't manage to match it. Of course, in principle, they are this expression here is the same as as this expression here, for example. But you see, this F of minus something doesn't appear anywhere here. So Lean is having some trouble actually understanding that it matches. Yes, sometimes there's some steps which are trivial, so they can be done by REFL, but you still need to do them because maybe it's trying to do some match with the actual syntax that it sees and not with the underlying type. Okay, no, I probably did something here. Okay, yes. Also, the indentation of calc. Now, the important part of the indentation you see is the start of each line. So it shouldn't start, for example, like this. Oh yeah, but it works. Okay, sometimes it complains if you start before, but apparently it's. I think the last version of Mathlib are a bit more robust to this. So it accepts even like less careful indentation. Okay, let's go on and let's see some other exercises with some quantifiers. Now that's basically not anywhere. There's nothing different mathematically from before. Here we're still using a quantifier, a universal quantifier, to say that a function is non-decreasing. But the difference here is that we're introducing two variables at once, and that's just syntactic sugar. So this, for all x1, x2, we're saying if x1 is less than x2, then the same order relation is maintained in the images. And we can introduce x1 and x2 at the same time. We could have also done something like this. So we could have written for all x, then for all, for all x1, then for all x2, etc., etc. But Lean allows us to introduce them at the same time. And when we need, now the second definition is, of course, the same thing with non-increasing. So it's the other way a function can be monotone. And if we need to use, maybe to unfold this nested for all, it's exactly the same as having more than one for all statement, one inside the other, where we just introduce the first variable x1 and then the second variable. And then again, you see we have inside here, inside non-decreasing. So if we did unfold non-decreasing, we have two universal quantifiers and then one implication, and that's the thing that's introduced with this h. But again, we don't need to unfold it manually; it understands it by itself. Here we use some forward reasoning, so we're using have to state something that then we want to use to conclude our goal. In this case, so we're going to prove that two non-decreasing functions, when nested, so when composed together, are still non-decreasing. And what we do is, okay, first let's specialize the fact that f is non-decreasing to these two particular inputs, which are x1 and x2. And that's what we're doing here with this have step one. We're saying, okay, since f is non-decreasing, specifically for x1 and x2, this means that the images of x1 and x2 are in this order. And then we do the same thing, but with HHG. And here you see that Lean actually understands right away that G composed F is is just G of f of x. In this case, f of x1. If we didn't know how this was defined, maybe it's just a new some new stuff that we're looking at for the first time. What we can do is now, of course, there's a special symbol here. Okay, so if we had just non-decreasing, we could do unfold non-decreasing, but can we do like unfold comp, which is the comp should be, yes, the symbol. As you can see, it doesn't work for notation. Unfold cannot be used with the notation, so we need to know the name of the underlying function, which in this case is the composition. And to do this, we can just hover over the symbol in the info view. So we put our cursor over that and we click, and it will tell us, oh, this is just an application of comp with all these parameters. Here, it will automatically put every argument as an explicit one. In fact, it puts the at before, which means take every argument as explicit. So it gives a lot of arguments that we normally will not want to give to the function, which are R. These are probably these are just the three types that are involved. So the type of the first function will go from alpha to beta. The second will go from beta to gamma, for example. And these three types are all R in this case. And then it gets applied to G and F. And if you want to unfold it, we can just write unfold comp. And as you can see, it gets unfolded. Now we don't have the symbol anymore. We just have the definition of the composition. And then we finish by exact. Okay. Another way we could have done this same exact definition proof is using specialize. So in this case, before we used have, just to take one of the hypotheses we had and to specialize it to a particular case. So we didn't do any complicated proof here. Just applied an hypothesis to something that we already had more explicit. Now this step can be done like, slightly more compact way using specialize. We write specialize, then the name of the hypothesis that we want to specialize, and then just the arguments as if you were to apply the hypothesis as a function to those specific arguments. And it has two slight advantages over have. The first is, you see, it's we have to write less things. It's a bit more compact as a notation. And also, it doesn't leave HF as a hypothesis. You see here, HF gets converted to the new this new hypothesis. Of course, we can use it only if we don't plan to use the original hypothesis many times, because sometimes we need the original hypothesis specialized over many different inputs, and then specialized will not help us. We have to do something like HEP, for example. But in this case, where we don't need the hypothesis anymore, it's actually useful not to have it in our context, because then we can read things faster. It's easier to browse the context, and especially if it gets for like more difficult proofs, the context can get really really long. So we may want to delete some hypotheses that we know we're not going to use. Okay, and the rest of the proof is just the same. This step has just been substituted with specialize, and the rest is instead of step 1, which is the new name we gave here we use HF, which is the old name that we can now use with the new hypothesis. Okay. Another way to put to compress even more this proof without even having to do any middle step is just by giving the the specialized proof step explicitly. So in this case, what we're doing is this proof probably did not get written from scratch in this fashion. It was probably written more like this, and then compressed into something more compact. How? For example, let's try to do it like in here. So here we notice that we're using something that was just modified once. So maybe instead of using the modified thing, we can give explicitly the modification without doing it explicitly before. We give it explicitly at the end. So we can comment this line. We copy this, and we put it in parentheses here, and it works. Now this practice of taking a proof and making it shorter is usually called golfing. That's a practice in general in computer science. This is called golfing because in golf you have to reach your goal in as few steps as you can, because you have to put the ball inside the hole as early as you can. And the same thing is can be sometimes useful in code. Maybe you want to find the smallest program, the shortest program that performs some kind of algorithm. It can also get competitive. There is competition of golfing that get pretty extreme with very, very like specialized languages, and that's not very advised. Like, do not over golf things in like when you write code, because they get very hard to read afterwards. But at the same time, it's also hard to read a proof if it's too long, and maybe there's a lot of repeated details that don't really need to understand the proof. So once you finish your proof, you may want to do some golfing to make it shorter and more compact, but you may want to restrain yourself from doing too much golfing, because you still want to make the proof as explicit as possible, as readable as possible. The first time that you formalize stuff, you will probably tend to make things very long and not to golf a lot. So that's something that you can also just avoid doing for your first formalization exercise and projects. But later on, you will see that it gets more and more useful, because you want things that you can see in just a few seconds, and you want to see as many stuff as you can in little time. Okay. Again, okay, we're doing the same theorem again in another way. Now this other way is even longer because we're using 4 lines of code this time. But it requires very little effort to do because we're using apply. And you see in the first in the examples before, we always put the explicit parameters. So we always wrote x1 and x2 here, also here, also here. Using apply instead, we can just tell Lean, okay, try to figure out what are the correct parameters that want to apply this function to. And here we can just reason, okay, we have g, which is the most external function here. So we basically have g applied to something should be less than g applied to something. So we can just try, okay, let's try to use the non-decreasing hypothesis. And we say apply hg, and Lean will prompt us to prove the hypothesis of this implication here. Again, we do the same thing with f, which with f. So with hf, we do apply hf, and then we're just left with proving that x1 is less than x2. But then we have this as an hypothesis, and we just use exact with the hypothesis to conclude. Another thing that I don't, okay, yes, it doesn't get suggested here, but it may sometimes be useful is if I know I have an hypothesis already in the context explicit, and maybe I don't want to type it out. Maybe I have a long context and I don't want to go look for it. I can just write assumption, and assumption just looks through the context and tries to match every hypothesis with the goal. And if it finds something that matches the goal, it closes the goal without having to spell it out manually. It sometimes can be useful to save a few seconds from looking.
If you write the code for Mathlib, what's the recommended? I mean, would you use assumption? Or would you use?
I will probably not use assumption actually in Mathlib. I'm not sure if it appears because there's conflicting views into what's the best balance of like explicitness to put into Mathlib. We can look at GitHub Mathlib 4. We can try to look for assumption if it appears a lot of times, like here. No, I wrote it wrong. Yes, apparently at least somewhere it's used, so it's not. It's probably not so slow because, of course, if a tactic is very slow, then that's a strong incentive not to use it. Assumption is probably very fast because it just needs to try all the very few things that you probably have in your context, so it's probably okay to use it. There was some discussion even recently on how much should you use tactics that maybe take a bit of time but make the proof much more readable and much of course even faster to type. For example, there's the linearity tactic that solves some linear arithmetic goals, and it can be a bit slow sometimes, but it can save you from like 4 lines of unreadable applications of lemmas.
It's more like write the tactics and so that is most readable and stuff like that. And then I can extract the proof term and then give the proof term as a cache to like witness.
So that's
perhaps invalidate the cache and change the tactic
that's a bit of a problem with maintainability because maintaining a proof term when lemma names change, for example, it gets really hard. So that's usually not something that's that people want to do. And also it becomes basically unreadable. So at least for the current tools that we have, we do not have a way to hide a huge proof term, but in principle that's possible. That's possible just to like say in some way that here I use maybe this specific tactic, but I'm not running it again every time. I'm just running the underlying proof term that I keep hidden. But yes, that's a problem for maintainability. But there's a middle ground here because there are some tactics that manage to produce not only the proof term, but some verifiable certificate that's way shorter than the proof term itself. For example, if we write, okay, one of the most powerful tactics is ESOP, written ISOP, and it's basically an automatic theorem prover that tries to do some kind of search on the background, and it can solve some non-completely trivial stuff. So sometimes it's actually useful in the development process. But of course, doing a search, it's slow. So you can write now here, probably going to work because it just needs to match an assumption. We can write ESOP ? And then it will suggest me a series of lower level tactics that still manage to prove the goal. So it doesn't provide me the full proof term. It provides me some tactics which are easier to maintain because they're probably not like 20 lines of unreadable code. So that's something that's actually done pretty frequently. In this case, you can just click on this and it gets substituted with your tactic. Sometimes ESOP produces like a certificate that's a bit too long and it does some unnecessary stuff. So you will need to goal fit manually afterwards, for example, to remove some lines that are completely unnecessary. But also other tactics also do this. And that's very much accepted. That's done like all the time. But yes, it's always possible to get to the proof term. And now I don't remember I never needed to do this, but there's a specific command to do it because of course every tactic produces a proof term. That's necessary for the kernel to ultimately verify the proof. I mean, the kernel can only verify proof terms. There is nothing else that it reads. So everything must be converted to a proof term. But yes, as I said, I don't think anyone actually uses it for development other than maybe some debugging problems.
Yeah, I was thinking perhaps there's some challenge behind it, for example, would just manage the proof terms and like cache them to speed up checking. I wouldn't speed up. I would just program tactic if a name or something changes, the cache validate it, it recomputes proof term, and then gives it speed up and that stuff.
Yeah, that's certainly something that's possible in principle, but we still have the maintainability problem, which can, in principle, that could also be somehow automated. So if we had, like in a perfect world where we have like perfect tools for development, this may probably not be a real issue. But for now, it kind of is. Okay. So where were we? Oh, yes. So we're the section finding lemmas now. So I told before a few ways to find a lemma that you maybe know kind of what you're looking for, but you don't know the name, or maybe you know the name, but not the full name. So like maybe the first part of the name. But what if I want to make the system look for a lemma by itself? Well, of course, one option is the lean state search. As we've seen, we can just paste the context. But fortunately, Lean provides also some integrated tools that try to do some library search for us. Okay, here we're going to see. Okay, here it just does it doesn't provide us already completed examples, but only exercises. Okay, so I will try to make them live. This should be really, really easy because I guess that simp, for example, will solve this in one line. Let's see if it's true. Okay, no, it doesn't. Maybe you have to provide like the hypothesis. Yes. Okay, so what's happening here? It's introducing two different tactics from before. The first one is simp, which stands for simplifier. And the simplifier is one of the most useful and widely used tactics. and it tries to simplify your goal in some way. How does it simplify it? Well, it has a library of what are called the simp lemmas, which are lemmas that it can use freely. It always knows the simp lemmas, and simp will automatically try to apply every simp lemma it has in the library to the goal and see if some of them match. Now, of course, not every lemma will be tagged with the simp attribute, because that would make simp very slow, but there's many situations where we need maybe lemmas that are not useful for everyone, but just in our specific situation. For example, if we have a specific hypothesis that's not going to be in the simp library, but it's still something that we can tell simp to try and use just by putting it between the square brackets after writing simp. So simp out of the box already works without writing anything. In fact, if we just do simp, you see the goal gets converted to just x is in x. And before we had this more complicated expression, but simp already knows that, for example, if you do the union of the intersection and the difference between two sets, you're just going to get the first set. So it does this, and now we could finish by putting exact hx. How is it called? Okay, yes, it works. But simp also can also try not only to simplify the goal, but also to close the goal. So if we pass explicitly hx, it will try to apply it and succeed. Now, simp is both, as you've seen, can be used inside our proof, so just to modify the goal of our proof, or as a finishing tactic to close the goal. One thing that's now, it's not completely necessary, especially if you're not doing something that's going to be maintained long after. But if you're planning to maintain your code, one important thing to do is to avoid writing simp inside the proof, because you can do it, but it's brittle in the sense that the simp library changes over time because lemmas get added or removed from the simp library. So simp can become more or less powerful. Usually it becomes more powerful over time because usually lemmas are added to the simp library. And so it can happen that you have your simp here that does not close the goal, but after some time, it manages to close the goal automatically. And so you'll get an error in your code, and you'll have to maintain it afterwards, and maybe every bump, so every time you update your dependency from Mathlib, you'll have to spend a lot of time changing things manually. But of course, you can still use simp. There's still a way to use simp inside the proof, and it's just using simp question mark. And this is basically the same thing as with ISO question mark, where simp question mark basically produces some small certificate that that does exactly the same thing that simp did out of the box. In this case, it writes simp only. Simp only means I'm not going to use the whole simp library, but only the lemmas that I write here explicitly. You can, I didn't say that, but you can both give hypothesis or actual lemmas inside the parentheses, and I can give more than one just using the comma to separate them. So I can use simp only these two things. So simp will not look through all the library, and this has two effects: that it's faster because it doesn't need to do the library search, so it's also convenient for efficiency, and it's way less brittle because now if some lemma get added to library, my proof will not automatically break when I update. Okay, now let's see another application of the question mark, but which is a completely different thing. Because as we've seen in simp and also ESOP, the question mark is used to make the tactic produce a simpler tactic that does the same thing as the strong tactic. In the case of apply, instead, it prompts the tactic to do some kind of library search. Let's try it. And you see, it takes a bit of time, and it looks through the lemmas of the library and it tries to close the goal. Now, actually, here it manages to completely close the goal. So here we're proving that if I have a continuous function with compact support, then there exists an x such that f of x is minimal, basically. For every y, f of x is less than f of y. What we're doing here is asking Lean, okay, can you find something that closes this goal? And it manages to close this automatically, so we're happy and we don't need to change anything here. But it can happen that it doesn't manage to completely close my goal. Let's see if it, it doesn't prompt us to do this. Let's see if I had to use apply here, for example, if it works. Okay, yes. Here, it doesn't manage to close our goal. Instead, it proposes us several different applications of various lemmas that it found in the library. And maybe one of those lemmas will be useful to us. The useful thing is it doesn't just give us the lemma because it would be unreadable. It also gives us the resulting subgoal. So it says, okay, if you try to apply this lemma, you will get this subgoal. This doesn't look any more useful than we had before. But if we go here, now this looks simpler. Now we have to prove that x is in x intersection y. In the third case, we have to prove that x is in the difference. Actually, none of those are going to work for our case because you see, let's try, for example, to substitute this. Now, don't worry about what's written here. It's just the application of this lemma. We could have written apply without anything, and it's the same thing. But now it's false. Now this is a false theorem because apply can get too greedy and it can try to apply stuff where we don't have the hypothesis met. In this case, we have that x is in x, and it's asking us to prove that it's in the intersection of x and y, but why should it be true? I mean, with this context, it's impossible to prove it. So yes, be careful when you use apply, but sometimes it can save you a bit of time looking for stuff. If you just want to close the goal, so if you don't care about things that try to simplify the goal, but you only want something if it manages to close it, you can also do exact question mark, and it will try, and it will only stop when it finds something that closes the goal, or if it times out. In this case, it just timed out. It took too long, and in fact, here it didn't manage to close the goal. But in this other case here, if you write exact question mark, it does this exact same thing as apply question mark. So apply question mark is strictly more powerful than exact question mark in exactly the same way that apply is strictly more powerful than exact as a finishing tactic, for example. Okay, I guess we finished the file. Now there's just two example exercises, I think. If you want to try and do them, or if you've already done them, we can we're also 15:18. Yes, I guess we can do a break anyways, like 15 minutes break. So if you want to try and do the exercises, or if you have other questions, I'm here. Okay, we can go now to the last exercise sheet, which is the fourth one. Okay, here. Okay, here we are. Now here we introduce like probably the last super basic objects that you will need to orient yourself inside the Mathlib library. There's of course a lot more definitions that are useful, or techniques or tactics that are useful to know. But once you concluded this file, you can at least read a lot of the files that are both in Mathlib or in some other project. So it starts with the conjunctions. So conjunction means we, for example, we want to prove this and this. And the symbol for the conjunction, so the symbol for and, is this logical symbol here that you're probably already familiar with in some way. we actually already saw something that is basically a conjunction, which is the if and only if, because as you saw, if and only if is just the conjunction of the two directions of basically the two implications, and it behaves just like any other conjunction. So let's see what we can do if we have a conjunction. In this case, in this example, we see both a conjunction in the hypothesis and in the conclusions. So this is a very like logical statement. We don't use any mathematical object. We're just dealing with the abstract propositions and implications between those propositions. So we have these two implications as hypothesis, and we want to prove these implications as a conclusion. So the first thing we do is we introduce the left part of the implication. And now we're left with two conjunctions, one in the goal and one in the hypothesis. So first of all, let's try to somehow handle the conjunction in the hypothesis. And we can do this using the R cases tactic. The R cases tactic takes our hypothesis as the first argument, and then it has a special syntax using the keyword with. And after with, we put some kind of pattern into which we want to unfold the first hypothesis that we gave. So what happens here is that HPQ is of the form P and Q. And so when we unfold it, we explicitly write out the pattern of the conjunction, which is written like this, with these angle brackets and a comma. Now the angle brackets can be written like this, so backslash and minus, and that's the left one, or backslash and bigger than, that's the right one, or we can write them both at the same time with backslash, smaller than, bigger than, and we do them in one go. Then HP and HQ are new names that we're giving to the two new hypotheses that we have, because of course we're starting with P and Q. We want to break it down into one hypothesis that tells us P and the second hypothesis that tells us Q, and we give the name HP and HQ. Then how do we handle the end when it's in the goals of our theorem? Well, we do exactly the same thing that we did when we were proving an if and only if statement. So we use the constructor tactic. Now, constructor again takes some kind of goal. It's actually a bit more general than this, but in this case, we're looking at just something that is composed of two statements. We have to prove both statements in our case. So it breaks the proof down and it branches it into two branches. So we use this dot notation to separate the branches. This is the first branch. You see here we had to prove R and S. Then in the first branch, we only have to prove R, and we prove it explicitly with the exact. While in the second branch, we only have to prove S, and again, we do it explicitly with exact. Now, we didn't really need, so again, we're looking at the same example here. We didn't really need to break down this have in the hypothesis beforehand. There are ways in which you can use it without breaking it down. So now it does two things at the same time. So let's do them separately. First, let's see how we can avoid using R cases. In this case, we still do constructor. So we branch, and we divide the proof in two branches. Okay. So if I want to prove R, here we have P implies R, and then we have P and Q. So what I can do is exact, or maybe let's do apply, because that's like more close to what one would do when he develops the actual proof. So you can apply H. So H is this implication here. So it prompts you to just finish the proof showing P. And then we can do exact we look for the name of the conjunction HPQ, and then we write .1, where .1 means I know that HPQ is made of two things. Just take the first one. Okay, you were asking something. Okay, sorry. Of course, the same can be done for the second branch. So we can do again apply, in this case H prime, apply, and then we do exact HPQ. This time we want the rightmost part, so we write .2. But here it does something more. So not only it avoids writing the R cases to break down this hypothesis, but it also avoids to write the constructor to break down the conjunction in the goal. And it does this in a similar way that we did here. So it explicitly gives us the pattern that corresponds to the conjunction. But in this case, with the R cases, we're given the pattern so we can undo it, we can break it down, and we're using it just to specify what the hypotheses are, what the names of the hypotheses are, what they should be. In this case, we're doing basically the opposite. We already have the hypothesis at hand, because for example, let's golf this a little bit. We wrote apply and then exact, but we're just doing exact a single thing, so we can just put the thing we did exact with as an hypothesis, as an explicit hypothesis of the apply, and now this can be this can become an exact. We can do the same thing here. Exact. Okay, so now we have two proof terms for the two branches. Instead of calling constructor and proving them separately, we can write them out explicitly with this angle bracket notation. And inside the two parts of the angle bracket, we put the exact proof terms. You see, this is the same as this, and the second one is the same as the thing we put on the right. We could have also, okay, it probably doesn't introduce this, but in the spirit of golfing things as much as possible, we could have also avoided writing intro in here, because as you know, an implication is just a function. So instead of writing intro, we can write the explicit function notation. Now this is just the lambda function notation for anyone who knows what a lambda function is. So we can write fun, in this case, that's the keyword for the lambda notation. Then we introduce the variable that we want to call HPQ in this case, and we write map. Also, this arrow here can be also written explicitly with an equal sign and greater than. That's the same, but map is more compact. So I usually use map, but also the other notation is also used in Mathlib generally, so it's okay. And this is, you see, a single proof term that does everything that was done in these 4 lines of code. So it introduces the name HPQ, and then it gives us back the proof of the conjunction of these two propositions. Okay. You see, it tells you can choose your own style in the next exercises. So here you can choose whether you want to unfold the proof using more tactics or compress it down like in a single proof term. If you want, you can try to like do a single proof term maybe after you already have a working proof of maybe using easier tactics. Here it introduces a new tactic, which is called Tauto, which is super powerful. And it basically tries to solve a lot of goals which involve implications, conjunction, disjunction, so all the logical operators. If your goal can be inferred maybe from your hypothesis, just putting them together as logical propositions, Tauto will probably solve your goal. In this case, you're just trying to solve some complicated implication between proposition, and it does this in a single line of code. Now, Tauto has the slight issue that sometimes it's a bit expensive to run, so it can be a bit long. So maybe you don't want to use it too frequently. If at least if you see that it takes more than a fraction of a second to run every time. Okay, now we go to another type of quantifier, which is the existential quantifier. Now, the first thing that the exercise tries to show us is how to handle an existential quantifier when it's inside the goal. So here we just have to prove that there exists some natural number n such that 8 is equal to 2 times n. Now here we could have also omitted the n as like the type of n, and Lean in this case will correctly guess that it should be a natural number. That's a bit of a case. That's just this special case that works because natural numbers are the first thing that Lean tries to put in if it doesn't know what the type of something should be, because they're basically everywhere. For example, if I write 0, Lean will automatically guess that I'm referring to the zero as a natural number. If you want like other types, you will often have to write them down explicitly, unless in the statement itself there is some reason that makes it obvious that a certain variable should be of a certain type. For example, if we have a function that takes a complex number and the variable x is an argument of that function, then Lean will automatically know that, okay, that can be only a complex number. It cannot be anything else. Okay, so how do we handle an existential statement in a goal? Well, basically, we have to provide some number n, and we have to provide a proof that 8 is equal to 2 times n. So here we provide the number, writing use, and then the number that we want to substitute to n. In this case, it's obviously 4. And Lean manages to prove that actually 8 is equal to 2 times 4 completely automatically. We don't even have to write refl, for example, because it tries to use refl after we wrote use, actually. So it does in the background without even us asking. But for more complicated proofs, after we say use, we just go on with the proof of the rightmost thing. Let's see if we have an example of this after. Probably inside here, you're going to look at something like this, but I will leave that as an exercise. And here, yes.
So does your example with 8
Mm-hmm.
does it work with any, like if I write, some much larger numbers, so is it going to become a super slow at some point, or?
Let's see if it actually is. Probably yes. If the complication is non-trivial, I think it becomes a little slow, because I mean here I'm not sure we can get to big enough numbers so that just the multiplication gets super slow. But if you have to do something a bit more complicated than multiplication, for example, there's computable functions that try to break a number into its prime factors, or some other complicated algorithm, and you can write an existential statement with that. I guess it will try to compute that in some way. I'm not sure it will work out of the box with refl, but if it does, it will probably get slower and slower.
But I mean, what is 8 billion? What is it for Lean?
So natural numbers are defined inductively. I'm not sure how the notation is explicitly given. So I don't know how it's handled internally. Okay, well, if we go into n and we open the documentation of n here,
is it that fast to produce a proof term that?
Now here I'm not completely sure that it needs a proof term. So short answer, I don't know, I'm not sure. But it may be that for some reason this two things are interpreted as like the same thing, like the same object. I'm not sure if this is true though.
Like usually inside theory, the way it works is that you have a bunch of definitional equalities, which are the one given by your definition, and all the terms when you write, you wanna like verify that the term has a certain type. There are a bunch of definitional equalities which just get applied, and it turns out that if the definitional equalities are given a systematic and theoretically one manner, every term has a normal form. So like before trying to see something at a certain type, we will normalize the type and see if it was. So like it will take 8 blah 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 to blah 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 substitute 4, normalize multiplication by definition reduces to that, and then involves potential expressive multiplication. But then the goal becomes 8 blah 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 equals to itself, which is true by one. So like in usual type theory, it works like that. And like type checking then involves computing normal forms, which is arbitrary expressive multiplication.
So, but the normal form is probably correct, or is
it is a method theorem that every term admits a unique normal form. So you can find number steps.
about this particular implementation of the normal form of the natural numbers? Is, how do we know that there is no
like how do you know the multiplication is correct?
yes?
Well, you have given us some definition of some point of multiplication in the code, and it will expand according to your like. Usually, in theory, natural numbers are implemented as an intensive type. As I was saying, so you have 0, then your successor when for every n.
Yes, it would require to build the billions of natural numbers.
Yeah, and the bad news is that by default, like this inductive definition is essentially realized computation is in place. You got 0, that's successor, that's SSS.
So it doesn't mean that this is what happened.
Yeah, it's usually one that for basic types of like natural numbers has a low level optimization, which like.
But if you add 6 more zeros, it should.
Let's try this. Looks like it's still going to work even if you put a crazy number of zeros. Maybe there's some other kind of optimization going on here. I don't know. Natural numbers are handled in a very like native. They're one of the first things that's defined in. They're not even defined in Mathlib. They're defined in Lean itself. In fact, if I want to explore this, I'm not going to the actual definition. It gets me to some random prelude page, which doesn't give me the definition of natural numbers, probably because they're a bit too low level to actually see the definition.
I think like big integers, so big stuff like in Python stuff should be able to handle such a multiplication.
Yes, but my question is, are you relying on, say, Python's implementation? Is there a proof that?
No, no, we're not relying on any external code from Lean. If there's some optimization going on, the function that does the optimization is written in Lean, and there's definitely a proof that this function is equal to other. I mean, otherwise it wouldn't type check here. It wouldn't. So there's must be something somewhere that tells us that these two things are the same. But yeah, I'm not sure how it's implemented down to the details. I don't know. But yes, it seems unlikely that even if it takes just one single operation for every step, it's not possible that this number gets like explicitly put out with the inductive definition anytime. So it will probably handle it differently. Maybe it really does some kind of multiplication with the digits or some other implementation of it. Yes, I think the multiplication operator is originally implemented as like the inductive version you would do in as the first thing you define after you define the natural numbers. But there's probably some other implementation. Probably one thing that's possible is the new implementation is the one that's by default that's used when you write out the multiplication and it tries to compute it. No, I'm saying maybe there's another implementation that's faster, and this may be the one that's automatically get. Mm. Mm. Okay, so apart from the huge numbers, we've seen how we can solve a situation where we have exist in the goal. What if we have exist in the statement, so in the hypothesis? So we have to use it as an hypothesis. So saying that then there exists something such that some hypothesis is basically can be broken down into an example of the thing that exists and a proof that that specific example meets the requirement of the existential statement. And the way we can do this is with the same tactic that we used before. That's the tactic used to break down the conjunction statements, and that's our cases with the same exact notation as we had with the conjunction. In fact, we can just say our cases the hypothesis where we have the existential statement, then with, and we give a pattern that's the exact same pattern that we had with the conjunction. In fact, this is basically a dependent conjunction where the type of the second thing depends on the specific element that we choose as the leftmost thing. And we can see here that we have now we have after these R cases we introduce K0, which is a natural number, and a proof that K0 meets this existential statement here. And then we just close the goal like we did before. So using the already known tactics like rewrite here, we just rewrite the n, and then we conclude with exact. Okay, let's see. Here we have an example that puts together a few of the things that we've seen. So we have both the if and only if and the oh no, sorry. We don't have sorry. The if and only if was only the definition of the divide proposition. So we have existential statements both in the hypothesis and in the thesis this time, because A divides B is defined. It says here is defined as there exists some number such that B is equal to A times that number. So in this case. Let's see. Okay, these are just examples. Well, let's solve these examples. I will solve this live here now. So how can we do this? First, we can unfold our hypothesis. So we can use our cases H1 with, and then we can give some names to it. If we're not sure how to call them, because maybe we're not sure what they are going to be, the thing we can do is we just put underscores here and then we go after. And Lean will automatically assign these blind name variables, so we cannot access those. These are, I cannot write W, for example, it's not accessible to a user at the moment, but I can see, okay, the first thing that's introduced is an integer, and the second thing is some kind of proposition. So maybe I can call the integer k, and then hk. There are reasonable numbers for integers, and this, I mean k's, and hk is a reasonable name for a hypothesis. And then again, our cases, h2 with, and then now we can call it, I don't know, m and hm. So now we unfolded the hypothesis. We can also unfold the goal of the proof, And to do this, we click here and we say that the definition we're looking for is dvd.dvd. So divide.divide, and write unfold divide.divide. But here we get into another definition, so we can do, okay, let's try and see if this works. Unfold again. And then we get into another complicated proof term, which maybe we don't really understand what's going on. So something that we can do instead of doing unfold multiple times is you can try to use simp. So simp out of the box doesn't manage to do anything. So it doesn't unfold or simplify anything. It tells us simp made no progress. But let's try this, simp with the name of the thing we want to simplify. So the outermost thing, so divide. And if we go here, now we have something that's way more, way easier to read, because we have an existential statement. It just tries to give some automatic name to the variable, which is C1 in this case. And now we can go on with the proof.
In this case, simp is equal to unfold, or because I'm trying to unfold the definition of the A divide C. But,
yep.
So I'm asking if
basically we can probably, I mean, after what simp does is first it unfolds this divide, which by default it doesn't unfold it, because so the different definitions can have different commands to make them easier or harder to unfold. And this is a choice of the people who developed this the specific function. And probably divide is not something that I always want to unfold, because that's something that's very recognizable. A mathematician knows what it means, and it's compact. It's easy to see. It's easy to parse, and even long statements which contain it. So I don't want to always unfold it. And on the other hand, if I really want to unfold it, and I do, I get to this int divide. Now that's not something I want to see. So this is probably marked as easier to unfold than divide. So if this appears, simp automatically unfolds this. So we get to this part here. But then simp does more. It also unfolds, basically, it also simplifies. I'm not sure if there's a way to simplify this just using unfold. Maybe not. Maybe there is, if we knew the name of the function that gets us the first argument of basically of a structure, but I'm not sure. And what we could do if we found ourselves in this situation is use simp again. And simp will actually, in this case, it will just do the last step for us. Because if you try to parse this basically says, okay, we have this structure here that only contains this field, which is called divide. And we are taking the first field, which is the only field that is in the structure. So basically, all this thing here is only the stuff inside. It's just this function. And that's a function that takes two arguments and gives us back the proposition, the existential proposition. Now, this function, what we do with it is we apply it to these two explicit arguments, which are A and C. But of course, a function which is written explicitly as a lambda function applied to the arguments is just the thing on the right with the meta variable substituted with the two concrete variables that we have here. And so simp only does this very basic simplification. I guess dsimp also works here. Dsimp is a weaker version of simp. Basically, it doesn't have the large library of simp lemmas, but it only applies things that you say only applies theorems that hold by reflexivity. So it only substitutes things when it knows that they are equal, because they are basically defined as equals. They are really the same thing. I didn't prove that they are equal. They are like already equal by definition, basically. And yeah, but dsimp will not work here. I'm not sure if it will work with divide. It will. Okay, yes, it does work even with this term, because basically everything we're not using any theorem here. We're just unfolding definitions. So simp doesn't need to go to the simp library. Okay, so after let's keep the simplest thing. So the simp, for example. Now we have to prove an existential statement. So what we need to do is first we use the use tactic to provide an explicit C1 in this case. So here we want C to be equal to A times something. Now we already know that C is equal to B times M. So here we have B times M, but B is equal to A times K. So here we would have A times K times M. And so here we have A times C1, which should be K times M. Now this is just, we can just deduce this like on a piece of paper separately. And we say, okay, use K times M. And now it prompts us, okay, now prove me that C is equal to this. So we can use rewrite. First, we substitute C with HM. Okay, then we substitute B with HK. And then we basically just need to use associativity. So we use mul assoc, which is the lemma that tells us, okay, multiplication is associative, and it concludes the proof. Maybe I didn't know that. So let's try if some of the library search tactics work here. And write exact question mark. And yes, it does. So it finds the exact statement that closes this goal. In this case, it applies it with an exact before we were trying to write with it. In this specific case, it's the same. Of course, if the statement we want to use is not something of the form A equals B, then we will not be able to rewrite with it, but we'll still be able to do exact. Okay. Okay, yes, I shifted a bit the break before, but I guess we can still do another, like, I don't know, maybe a bit shorter, 10 minutes break, if you want to try and solve these two sorries that are left in the file. Okay.
Quello che volevo dire è che io ti provo a fare e invece di usare simp, pensavo che quella definizione lì deve essere direttamente con unfold. Invece con unfold viene un po'.
Perché tu hai fatto fare.
Invece di dire alla fine del C.
Cioè tipo unfold dvd.dvd hai fatto?
Esatto.
Ok.
Cioè, quindi io credevo che ottenevo questo qui che c'è un che mi dice.
Sì, questo è perché il divide avrebbero potuto implementarlo anche con direttamente la proposizione. Per qualche ragione non l'hanno fatto. Come mai? Non lo so, probabilmente perché divide è legato a una type class instance, quindi ci sarà una type, diciamo, ci sarà una classe che dice divide, non so, R, per dire, ok, R è un tipo che ha un concetto di divisibilità al suo interno. Credo, adesso non sono sicuro al 100%, ma mi sembra ragionevole. E a quel punto vuoi dire, ok, in questo caso abbiamo Z, non R, quindi abbiamo Z, vuoi dire qual è la specifica istanza di divisibilità che tu stai usando in questo caso. Quindi divide funziona per qualsiasi tipo. Nel caso di Z ti sputa fuori la specifica divisibilità che sta in Z, e quindi la divisibilità di Z è scritta in questa definizione inst divide int. Vediamo se me lo fa cliccare. Ah no, ok, l'info view dalla versione online evidentemente non funziona per fare, salta la definizione, però sì, verosimilmente è una cosa del genere, ma in questi casi appunto cioè spesso le definizioni di livello un pochino più basso, specialmente se hanno dei nomi brutti, tendenzialmente se gli fai un simp hai buone chance che questa venga, diciamo, srotolata in maniera ragionevole, perché sì, diciamo, nessuno vuole vedere normalmente
Se no che
corregli scritte sul portafoglio view. No, infatti. Mhm. Sì, è che di fatto qui è praticamente una definizione ausiliaria per... Mhm. Sì, sì, no, ma è la cosa normale da fare, solo che uno poi magari vede qualcosa di più basso livello e provi a srotolarlo in altri modi per renderlo, diciamo, la cosa che chiaramente in questo caso ti aspetti, poi in altri casi non sai neanche cosa ti aspetti, quindi chiaro, è più difficile perché non sai se sei arrivato al livello base e lì devi veramente semplicemente metterti a capire cosa c'è scritto e dimostrarlo, o se invece è semplicemente sporcizia sul, diciamo, notational junk e ti vuoi arrivare alla proposizione scritta in modo pulito sotto. Una buona euristica è provare a usare simp e vedere che succede nel dubbio, sì. Diciamo, provare a usare simp, se non funziona subito e se ti dice simp non ha trovato nulla, provare a dare come ipotesi a simp la cosa che vedi scritto. Perché magari, ecco, per qualche ragione non è segnato come un simple lemma il fatto di, cioè non è segnato come una definizione che può essere automaticamente srotolata, unfolded, però per qualche motivo per te invece dovrebbe essere srotolato, quindi gliela dai esplicitamente e speri che funzioni. Ecco.
In questo caso è tautologico, però se ci fossero delle visibilità un po' più complicate, potrei usare calc e in qualche modo usare la transizione.
Sì. Calc supporta, credo, out of the box tutte le proposizioni che hanno appunto per cui è dimostrata la transitività, direi, o comunque quelle più ragionevoli supporta, tutte le disuguaglianze supporta, la divisibilità proviamo, ma credo proprio che la
Cioè, noi ovviamente stiamo dimostrando.
sì, infatti, potremmo fare
Però
calc, anzi facciamo calc punto interrogativo così. Così e poi andiamo a dire, beh, giustamente calc è sempre particolarmente schizzinoso, ok?
a dividere
Diciamo tipo così, e poi ci mettiamo B. E qui vediamo se per esempio riesce a risolverla da solo. Sì, ci riesce. Vabbè, sì, giusto, è proprio l'ipotesi, ed anche qua sarà semplicemente H2 opzionale proof term. E lui sa già che la divisibilità è transitiva.
Prima Lorenzo ha trovato la pagina in cui si parla degli interi.
Ah, ok, sì, su l'implementazione di Lean o in type.
Pare che non sia dentro lì. Numeri grossi si appoggia a qualche.
Ah, qui si appoggia. Non scritta in Lean addirittura? Ah, ok. Ok. Evidentemente è uno di quei piccoli pezzetti di Lean, io credo che fosse quasi solo il kernel, però sì, evidentemente allora anche qui i numeri grandi sono implementati fuori dalla libreria, può sapersi. E avrà sicuramente comunque un modo per tradurre in un proof term di Lean l'uguaglianza, cioè addirittura potrebbe essere, cioè a meno che se è considerato parte del kernel questa cosa, forse è considerato parte del kernel, non so. Se non è considerato parte del kernel, credo che debba produrre un termine, un proof term per...
Se mai chiedo se me se gira la pagina. Non ho visto. Prova.
Ah, in the kernel, va bene. Ah, ok, quindi sì, proprio...
Vabbè, diciamo, erano il kernels.
Ah, infatti sono sia nel kernel che nel compiler che l'implementazione che riduce la... Quindi tutti i numeri fino a una dimensione più o meno praticamente...
Però dipende dalla tua architettura.
Ah, giusto. Perché dipende dalla macchina in cui sei specificamente. Quindi, sì, in effetti andava particolarmente veloce, un veramente grande, quindi pensavo che il fatto che lui sta facendo zero operazioni, sta proprio semplicemente, cioè, ha già allocati entrambi quei neuroni. Qui no, con zero operazioni prende comunque moltiplicare
Sì, cioè
direi il numero a destra per 4. Vogliamo riprendere?
Io tra l'altro preferirei andare via 5 minuti prima delle 5.
Allora, speriamo questo prima. Non è che non facciamo troppo nessuno. Okay. Okay, so for the last like half an hour, we're going to try and solve the probability part, like the probability file in Glimpse of Lean. This is one of the many files that you can find in Glimpse of Lean if you go here in the description. You can also open these online. If after the tutorial you want to go on and finish, for example, all the files, you may want to download Lean, install it in your local machine, and then use VS Code to solve the exercises. Or you may want to go on even more and not only solve Glimpse of Lean, but maybe study mathematics in Lean, which is a much more in-depth textbook. And it can also be found online. It can be found just Googling mathematics in Lean. Okay, you can go here and you have basically the PDF. You can also find the HTML version and the interactive version. Okay, so let's go, where are we here? And try to look at the probability file. So we can look at some like more advanced, more complex objects than just propositions and integers. And we can see how to use a part of Mathlib that maybe you don't know exactly. In this case, the part of Mathlib that we're going to use is the one with the namespace measure theory or with the namespace probability theory. And in fact, if we go here in the file, we see that the first thing we do is we open those namespaces. So we don't have to always tell measure theory dot something or probability theory dot something. And we also open the set namespace that allows us to manipulate intersections of sets, for example, and other operations between basic sets. With set, I said we're in type theory, so we're not in set theory. So what is a set? It's an object that can be defined just any other object in type theory in general, and basically it's exactly what we imagine as a set. So it's a collection of objects, but all the objects in the set have to be in the same type. So a set cannot be really any set that we can think of. We can get to that if we, for example, if we do the union of some types. So we can also do more like exotic sets if we want, but in the basic usage, we usually just use sets of a single type. And set is how we call not only like the whole set, but as in set theory, a subset is also a set. So a subset of some type, we still write set. Okay, let's start by seeing some new notation actually when we want to introduce variables that we are going to use in more than one single, maybe one single theorem or one single example. So let's say we want to talk about probability theory in general. For sure, we're going to fix some omega, which is going to be a measure space, and we're going to use it a lot of times, so we don't want to write it every time. So we introduce this as a variable. We give it a name. Omega type means just, okay, we have some random type, which we call omega, and then we put some structure on omega. So we're assuming that omega has the measure space structure on it. Let's see what it means to be a measure space. So a measure space is a measurable space equipped with a measure, referred to as volume. So measure space, that does not only mean that it can be measurable, but we're actually fixing a specific measure on this space. Now this measure, I think it doesn't. Okay, yes, it's written up here. This specific measure that we're introducing here is referred to as volume, but it also can be referred to with some special notation, which is this P here. So the blackboard P. If we write blackboard P, and we already introduced some measure space instance over omega, this is going to assume that this is the P over omega. And here we're stating that this measure is actually a probability measure, so it's normalized. It's not infinite and doesn't have some strange total volume, but the total volume is 1. Okay. We're also going to introduce some subsets of omega, and the notation is A and B have type set omega. And now we're going to define some conditions that, for example, independence of the two sets. Now, first, what it tells us here is when we're talking about measures, we always have to deal with infinite values when we are in the general measure settings. Of course, we shouldn't need to worry about it because we're in the probabilistic setting. But as you can see here, P is defined as a measure. So in principle, it is a general measure. And we could go and see the definition of measure. So we command click if you're on Mac, or control click if you're on Windows. You can go to measure spaces. You see measure. Here's the definition of what is a measure. It's quite more complicated than the definition we've seen before, because it's a structure. That's a way of defining stuff that bundles more pieces of information together. So we're not just telling, okay, measure is a single proposition, but measure is a collection of some data and some propositions. Here we can see all the things that that compose this structure. And what we're interested in now is this part here, which is the underlying function. Okay, a measure is basically a function that takes a set and gives us back some, we could say, real number, but in general, it's not a real number because it's this type here, which is ENN real. It means extended non-negative real. Extended because we should allow plus infinity when we're dealing with measures, and non-negative because, well, if we're dealing with measures, we don't care about negative values unless we're doing some signed measures, but in this case, we're not. So we can just work with non-negative values. Then there's also all kinds of properties for this to be a measure. For example, the empty set must have measure 0. It must be monotone and other axioms of measure. But that was just to see why we have this ENN real as the codomain. Okay, let's go back to the Link4Web interface. Anyways, here it tells us, okay, you have to deal with the fact that it can be plus infinity, but most things can be done in ENN real just like you do it in the real numbers. But sometimes you have to provide a proof that your number is not plus infinity. And it says here, okay, you can do it with this lemma here, which is measure not equal top. So that if you have a probability measure, you're not going to have as an output plus infinity. Okay, now we define what it means for two sets to be independent. And we say A and B are independent if the probability of the intersection is equal to the product of the probabilities. And here it prompts us to show some very simple properties of the related to the independence of sets. Let's try to prove one of them. For example, the fact that this relation is symmetric. So if I have index set A and B, then I also have index set B and A. And we do this in the usual way. We can use the tactics that we've already seen. We introduce the hypothesis. We call it H. Then we can unfold in the set. Maybe we want to unfold it at H and at the goal. And now we can do something like maybe the first thing we like to do is we switch PB with PA. So we use rewrite, mulcom. And after we do this rewrite, now we have something in the goal which is equal to something in our hypothesis, because we have here PA times PB. So we can use again rewrite with our hypothesis, but we have to use it in the opposite direction. So we put the left arrow here. And then we want to basically swap B and A with the intersection. So we'll need some lemma that tells us, oh, the intersection is symmetric, actually. Let's see if exact can do it. Probably cannot in this case. Let's see, but maybe it will surprise us. No, okay. It cannot because it knows that it can swap B and A, but it doesn't know that it can do it inside the P. So we have to somehow, or we can, okay, let's try two different approaches. The first one is we try to remove the P. So we're seeing two things which are equal, but some, the skeleton of the expressions on the left and right side are equal, but we have some details inside which are different. When we're in this situation, we can use congr. A congr means congruence, and it does this. It tries to look for things which are equal. It breaks down the expression, and it prompts us to prove that the single components are equal in the left and right. In this case, it doesn't work out of the box because it says, okay, now we have two goals. We have to prove that B is equal to A and that A is equal to B, because it sees these two things which look the same on the left and right. They just have different variables, and it breaks it down all the way down to the very variables. But that's false, of course. We don't have the fact that B is equal to A. So how can we do this? Well, we can limit the power of congr using, for example, putting a number after it, which is the depth that congr will basically destroy the definition, destroy the expressions. So congr 1 means, okay, just do it at depth 1. So just break the first thing that you see. And now we can actually use exact to close the goal. And now we also learn that the right lemma to use here is intercom, which makes sense because it's the intersection that's commuted. Yes?
You repeat what does congr?
Sure. So congr, we use congr whenever we have two things on the left and the right hand side of some of an equal sign in the goal. Okay, we have something equal to something. And we use it when the two things, so the thing on the left and the thing on the right, are in some way similar. Maybe they have a similar structure, but maybe the details are different. In this case, the similar structure is the fact that they are both P applied to something, but that something is different. Now, Congress sees that they're not only P applied to something, they are both of the form P applied to something intersection something, okay? So it tries to break down it. Whenever I said something, it substituted with a meta variable, and it tries to say, okay, the meta variable on the left is this, on the right is this, prove me that they are equal. Conger can be used, for example, if I have, okay, maybe I can do it with an example. If I have A, B, and C, which are real numbers, and I want to prove that A plus B is equal to A plus C, and I go into the proof, what I can do here is, okay, maybe I have the hypothesis that H, B is equal to C. Okay, what I want to do here is I just want to get rid of this A on the left, and I can do it by Conger, and it works. It's okay. Conger is a bit more powerful because it also tries to apply the hypothesis that you have. If it manages to, it will close the goal automatically. But if we didn't have this hypothesis explicitly, maybe because we have it's like in a lemma or something, then it takes out the A because it sees, okay, I have something plus something, but the thing on the left is not a meta variable. It's the same thing on left and right. So it automatically closed the first of the two goals that it would have produced and just prompts us to prove the second.
So if you do it with A plus B equals C plus A, it will give you the two goals, A equals C and B equals A.
Yes. Yes. So in this specific case, Conger is useless because it just the only thing it can do is make us is try to make us prove something that's false, which in this case is A plus C or B plus A. So maybe I need to massage the equation beforehand before I use Conger.
Why the one?
So the one, because the first thing that Conger tries to do is it reduces the expression to this, so it takes out the P. So it looks at the first level of abstraction. This is P. I mean, this is P of something equal P of something else. So it just, if you say, okay, just go one level deeper, it takes out the P and it tells us, okay, show me that something is equal to something else. But then I could use Conger again. It's a recursive kind of function. So it tries to apply itself as many times as it can, unless I put a limit to it by writing a number, and then it just tries to apply it itself up to n times, where n is just the number that I put here. Okay. Okay, so we've proven this. Now I will not prove everything, but if you want to try and prove some of these statements after this should be easy. I mean, you just have to apply the techniques that you've already seen. I don't think any. Oh yes, no, sorry. Here it tells you a new tactic, which is measurability. So maybe, yes, maybe we can try to do this. No, I'm not sure if it's needed here. Yes, it is probably. So let's try to do this goal. Because it introduces a powerful tactic that's a specific, like a domain-specific tactic that's called measurability in this case, and it's used to prove that things are measurable. So let's just do intro H. Maybe let's do unfold in depth set at H and then the goal. Okay, I have to prove these two things. What I need here, okay, yes, I need the measurability probably because I will need to say that this P of the complement of some set is 1 minus P of the set itself. And so I will need the measurability of B and the measurability of B complement probably. Let's try to see if we can do this. maybe we can do a have, so h1, for example, and we're going to say that p, oh no, this is bbp, p of b c, okay, the small c is written like this, is just equal to 1 minus bbp of b. Okay, then we can leave it as a sorry, and then we'll prove it later. So we can just try to see if it actually helps us solve our goal. So we can use now h1 here.
This hypothesis implies that BC is measurable.
Because we have that B is a measurable set in the hypothesis in this case.
Yeah.
Oh, okay, no, that's okay. Yes, that's okay. I understand. You're going to say, how can I even write P of something that's not measurable by default? Okay, so that's one of the quirks of stuff in Mathlib, is that usually if you have some function that you know only applies to a subset of the whole, maybe of the whole domain. In this case, the domain is the subset or the set of subsets of omega, but we know that the measure only applies to measurable sets. In this case, we can let's see if we can find again the definition. No, okay, doesn't matter. Basically, what is done usually is we still define the function on the whole domain, and then on the set that it shouldn't apply to, we just avoid them. It still gives us something, but it will probably give us either some junk value, or it will not satisfy most of the conditions that we find that we prove for, I don't know, measures in general. So a measure, for example, let's try to go in here and prove this. Now by exact, yes, exact works here in this case. So I want to prove this, and I found exactly the right lemma to do this, but it needs the hypothesis that my subset is measurable. But fortunately, I have it. Okay, so now it doesn't. Okay, it's probably not needed then. The fact that BC is measurable. Maybe it's enough to know that B is measurable in that specific case. In this specific case, but say that we had to prove, maybe in one of the later examples it will be needed. Say that I still have to prove that that BC is measurable. Okay. Okay. So if I'm in this situation, I could either use exact, and since we're in a very simple situation, it will suggest me actually some good lemma that works. But if we have some more complicated combination, maybe of measurable sets, exact will not work. But what will probably, in like many situations, still work is the specific tactic for measurability, which is called measurability, that knows a lot of measurability lemmas and tries to apply them to simplify my measurability goal. If I try to use measurability to solve something that's not a measurability like thing, it will just fail. You see, it tells us tactic ESOP failed because measurability actually is a variation of ESOP. ESOP is very general and it can be expanded with specific lemmas. And so the lemmas that are marked with the measurability tag will be used by this specific version of ESOP, which is, I mean, ESOP by itself will probably not be able to close this goal. It's definitely not this one, but maybe we can try it on this one. Okay, no, yes, in this situation, I mean, of course, in this situation, even exact question mark works. So it's it's normal that ESOP will work, but in some situations which are more complicated, ESOP will time out while measurability will manage to solve the goal. Oh, measurability can also solve some measurable function goal. So not only measurable set, but also measurable functions.
Is it common to have tactics that relate to specific domains?
There's a few. It's not for everything. There is a tactic. Unfortunately, maybe the more we have, the bigger library we have, the more we have like powerful specific tactics for specific situations. For example, there is one for continuity, which is basically the same as measurability. Now there is, maybe it's almost ready now. It's already usable, but it's still being developed a bit, I guess. A tactic which is called FunProp, which is to prove properties of functions. For example, it basically substitutes measurability in the case of measurable functions and also continuity, because it basically does the job of both of them, but it can also prove more general things, and it's faster. So because it's more optimized, measurability is not very fast. It can make your proofs a bit slow if you overuse it.
These tactics are not part of
I'm not sure where. So ESOP has its own like folder. I guess measurability may be inside of Mathlib. I'm not sure how it's handled exactly, but I guess measurability is in Mathlib, because there is. I mean, you can do something like import Mathlib. I think it's tactic. Yes, it exists. So there is a subfolder of Mathlib which is called tactic, which has many subfolders. Oh yes, we can even see if measurability is in there. Okay, you see that there is monotonicity. Yes, there is measurability between the Mathlib tactic, and these are inside Mathlib because there's
tactics.
I think most of them are written in Lean. There's a few examples that call external programs. For example, there's the polyrith tactic, which handles some arithmetic with polynomials, and it calls, I think it's Sage. Sage does some computation with some, I think, like Gröbner basis computations, and then it manages to produce some kind of a proof term that gets converted to a proof term in Lean. So yes, there's some tactics that rely on external tools. Most of the tactics, though, are written in Lean. Like even fairly complicated ones like ESOP or FunProp are written in Lean, because it's like there's a very expressive metaprogramming language in Lean that can handle even complicated things. Let's see if it's somewhere in here, but oh yes, there's apply@, apply conger. I'm not sure if apply question mark is a syntactic sugar for one of those. Maybe not. I don't know. It may be written in Lean, though. I think it's likely that it's written in Lean. I think that the general philosophy is let's try to rewrite things in Lean as much as we can, basically. So especially for like tactics and automation, it's encouraged to write things in Lean rather than external languages. Okay, maybe we have like 3 more minutes, and let's see what we can do in these 3 minutes. Oh yes, we can see an example of a new notation that we can introduce. In this case, we have the conditional probability of a set. So the conditional probability of a set conditioned to another set. And we can, of course, we can define it just mathematically. And we could just continue to use conprob in the library, in like whenever we need the conditional probability, but it's nice to have specific notations for certain things. For example, conditional probability has a very specific and nice to see notation. And we can very easily introduce this notation in Lean using this notation 3 keyword. And we just specify the notation. Everything that will be just notation has to be put between the symbols here, and then we can introduce variables A and B that get matched with the variable that we use here on the right-hand side after this arrow here. And at that point, whenever we write P of a condition to B, Lean automatically understands that this notation means conprob A and B. And we can unfold it. So we can unfold conprob, and it just gets unfolded to the definition of conprob. Or we can do simp, for example, conprob, and it will unfold it. Let's see if it will unfold it without the suggestion. No, it will not. It means that by defining things like this, we're telling Lean, okay, do not unfold them too eagerly. Do not try to unfold them every time you see them. Only if I ask you to actually unfold it. Okay. But now the last thing I want to show is this thing that's written in here. We talked about it before during the break, actually, with someone. But this notation is how we introduce new lemmas that can be used by Sim, and we introduce them with this tag here. So we write @sim, and this automatically gets introduced into the Simp library and will be used by Lean. And this is very important because, of course, we could have written just Simp. Like when we define the static Simp, we could have just hard-coded all the theorems we want to use, we want Simp to use. But that has a very like complicated solved problem. That is, what if I want to use Simp before I define the lemma that I want Simp to use, and I would need to get like circular imports, which are bad in general. And so how do we solve this problem is we use the tags. So we can just define the tactic somewhere, and then the tactic becomes more and more powerful the more in depth we are in the library. So the same tactic at the start of the library will be a weak tactic, but then it gets stronger. And the same thing can be done with measurability. So if instead of being a lemma about the condition probability was a lemma about measurability, I could have written measurability here, and this lemma would get added to the measurability library and then used every time I write measurability after this lemma. Okay, I think we can finish here. So thank you everyone for following the tutorial, and we'll see for each other for the final lecture tomorrow about AI and formalization. That's it.